Welcome to the ATA Chapter Channel. Today we're diving deep into the incredible engineering behind the Airbus A380's climate control. We're going to break down how this massive twin-deck giant keeps over 500 people comfortable at 35,000 feet, following the journey of the air all the way from the hot engine bleed to a perfectly tempered cabin. So here's our flight plan for today. We'll start with a big picture overview, then zoom in on the central mixer unit. That's where everything comes together. After that, we'll check out the clever recirculation systems, the super precise trim air system, and finally, the computers that command and control the whole shebang. All right, first up, let's just appreciate the scale of the challenge here. Keeping a twin-deck super jumbo comfortable is, well, it's a monumental task. You're constantly managing pressure, temperature, and airflow. I mean, look at this thing. The sheer size of the A380, with 2 full-length passenger decks, means one of the most advanced environmental control systems ever built. It's not just about comfort, it's about safety, pressure, and of course, doing it all as efficiently as possible to save fuel. At its heart, the whole system is doing this incredible balancing act. It takes scorching hot air from the engines, cools it way down in the air conditioning packs, and then it mixes that fresh, cold air with filtered air from inside the cabin. That final blend is the secret sauce for a comfortable, safe, and efficient flight. So, let's get to the core component of the entire distribution system. This is the central mixer unit. It's the meeting point for fresh air and recirculated air. Okay, if you look at this schematic, you can see the mixer unit right there in the middle, acting like a central hub. See the cold air coming in from the 2 air generation units? We call those the packs. That fresh air meets up with warmer, filtered air that's being pushed in by some powerful recirculation fans. You know, this mixer unit is so much more than just a simple box. It's specifically engineered to mix the air perfectly and act as the main distribution point. It's even got a safety valve, the MORV, just in case of overpressure. But honestly, the most ingenious part is a special design feature right at the air inlets. And this is where the engineering gets really clever. The fresh air coming from the packs can be literally sub-freezing. So to stop ice from building up right where the air mixes, these spiral housings take the warmer recirculated air and wrap it around the cold air. It's like an insulating blanket, a brilliant way to solve a problem using energy the system already has. Now, taking all that bleed air from the engines costs fuel. So to be more efficient, the A380 recirculates a lot of the existing cabin air. And it does this using 2 totally separate systems, a high-pressure loop and a low-pressure loop. This table breaks down the 2 systems perfectly, and you'll notice they're not just backups for each other. They have completely different jobs. The powerful high-pressure system pulls air from the main deck and shoots it right back to the central mixer. Meanwhile, the low-pressure system uses a bunch of smaller fans to handle the massive upper deck, feeding that air back into the system a little further down the line. The high-pressure system is the real powerhouse here. It pulls air from the main deck, runs it through hospital-grade HEPA filters, and its 4 big fans give it the punch it needs to feed directly into those clever spiral housings we just talked about. So it's also playing a critical role in preventing ice. The low-pressure system, on the other hand, it works more like a local booster. It's got up to 10 smaller fans that pull air from all along the huge upper deck. After it's filtered, that air gets put right back into the main supply ducts downstream. This just helps reduce the total amount of air the central mixer unit has to pump out. Okay, so now we have a huge supply of perfectly mixed, temperate air leaving that mixer unit. But how does the plane get different temperatures for different parts of the cabin? I mean, the cockpit might want it chilly, while a passenger zone in the sun needs less cooling. Well, that is the job of the trim air system. And the scale of this job is just massive. The system is managing 16, that's 16 independent temperature zones all at the same time. Just think about that. Every single one of those zones has its own unique temperature demand, and the system is constantly adjusting to meet it. So how does it do it? The solution is really elegant. As you can see on this schematic, the system taps off a tiny amount of hot bleed air before it gets cooled down. This hot air gets sent through its own little network of ducts. Then, whenever a zone needs to be warmed up, a tiny, precise amount of this hot air is blended into the cool air supply right before it enters that specific zone. And this process is happening constantly for all 16 zones. The main computer, the temperature control system, figures out what's needed. It sends that command to a dedicated controller, which then tells a specific valve to open just the right amount. It's literally trimming the final temperature for that one zone.
Now, before that hot air can be sent off to the different zones, its pressure has to be just right. That's the job of the two TAPRVs, the trim air pressure regulating valves. They make sure the hot air pressure is high enough to mix in properly with the main air supply, but not so high that it causes any issues.
And here is the absolute key to precision comfort. Each of the 16 zones has its very own trim air valve, or TAV. You can think of it like a dedicated computer-controlled hot air tap. The controller commands this little valve to open or close, adding the exact amount of heat needed for its zone and its zone alone. So, we have this incredible, complex web of fans, sensors, and valves. How is it all orchestrated? For that, we've got to look at the brains of the operation. At the very heart of the temperature control is the Trim Air Drive Device, or TAD. This thing is the workhorse. It's a dedicated dual-channel computer, and its only job is to take the temperature requests from the main system and turn them into actual, physical valve movements for the entire trim air system. This slide shows you the chain of command perfectly. Up at the top, you have the temperature control system application. That's the software that's running on the aircraft's main computers. It figures out what everybody needs and sends those commands down to the TAD. The TAD then takes those orders and makes it happen by controlling all the valves. And this all loops back to the flight crew, of course. From the overhead AR panel, they can keep an eye on the health of the whole system, set the master temperatures, and step in if they need to. It gives them a really clear, high-level view of this complex and automated system doing its thing. You know, when you step back and look at the whole thing, the complexity, the redundancy, the sheer precision of it all, it is truly impressive. It kind of makes you wonder. With its separate recirculation loops, a 16-zone trim air system, and layers of computer control, is the A380 system the absolute pinnacle of passenger comfort engineering? Thank you for watching. Please don't forget to like, share, and subscribe to ATA Chapter for more technical training.